For years, I've been curious about the stability of a three-wheeled vehicle versus a four-wheeled vehicle, or a three-legged stool versus a four-legged stool. So after years of occasionally wondering about this, I thought I would do something about it and try to figure it out. This is what I got. I'm going to do a quick overview so you'll know what to expect in the video and it'll all be clear hopefully. Take a stool right here of arbitrary height. I'll put the center of mass right here. I know I'm putting it at the top, but something or someone will sit on it, so I'll just arbitrarily call that the center of mass. You could always make this taller if you wanted to. Tip it over. When that center of mass crosses the edge right there, that'll be your pivot point, and then the whole thing will tip. What I'll show here is that something with four legs or four wheels could have a ratio of 2 to 1, but if you only have three legs or three wheels, it'll be a ratio of 2 to 0.58, which means it'll tip with only 58% of the force. What this makes here is a lever right there. There's the fulcrum, so you have a 2 to 1 ratio. If you have a lever that is just flat, like a seesaw or teeter-totter, and that's the fulcrum, you can flip up the long end like that, and it'll look like this, and you get the same results. So on a four-wheeled vehicle or a four-legged stool, you'll have a 2 to 1 ratio, and on a three-legged stool, you'll have a 2 to 0.58 ratio. Here's a better example of the lever model, I think. We have our lever. This end of the lever is 1 unit, that one's 2. We have some mass over here. Even though technically the middle of this mass will be right here, let's just say the mass has to travel 1 unit, or it has 1 unit for torque. Force times distance 1 equals force 2 times distance 2. So let's just say the mass creates a force of 1, the distance is 1, equals force, whatever force you have to push right there, times the distance of 2. So 1 divided by 2 is 1/2, or 0.5. And that's how much force it'll take to tip your four-legged stool. Now for the three-legged stool, we have 2 to 0.58. The mass on this end of the lever is only 0.58 units away. Force 1 times distance 1 equals force 2 times distance 2. The force again will be 1, but the distance is only 0.58, equals force 2 times distance 2, which is 2. That means force 2 equals 0.29. So it's obvious that I think initially that this is 58% of that, but you can also do the math here. 0.29 divided by 0.5 equals 58. So this will tip. This only requires 58% of the force on this lever to tip, so that this mass gets over the fulcrum and will tip over. I'll start with something quadruped, four-wheeler, quad bike, four-legged stool, whatever you want to call it. So we got the 2 to 1 ratio. I'm going to make this like a bar stool, and it's just an arbitrary height of 2. The base is 1. If you look at this from the top view, it'll make a square, 1 to 1, 0.5 from there to there. The center of mass will just be in the middle, and it has to travel 0.5 units to get to the edge where it can tip. Remember that 0.5 units. Now for a three-wheeled vehicle, or a stool with only 3 legs instead of 4, I did an isosceles triangle, so all the legs are equally distributed. It'll still be 1 unit from here to here as we look down up on this stool. 60 degrees for the whole angle there, 30 degrees for half of that angle. To get the center of mass, I just bisected the triangle from this center, from the midpoint of each line to the point, and they all intersect right there. I ain't no geometrist, but this to me looks like it would be the center of mass, because it is going to have equal area on each side from here to here to here. This will be equal area, this and this. So both the area will be equal and the angle will be equal, because these points will be distributed at 120 degrees from each other. 360 divided by 3 points equals 120 degrees. So this center of mass is symmetric in both area on each side and angle. To make an accurate equilateral triangle, I just took tan 60 equals opposite over 0.5. So this will be 60 degrees. Here's your opposite, there's your 0.5. Or you can do sine of 60 equals opposite over 1. You'll get 0.87 from here to here. And here's the interesting part. You can always tell if it's a math nerd because they get excited about the little things. We need to find out how far this center of mass needs to travel to get to the edge here so the stool can tip. So we got 0.5 from here to here. Let's find out that length right here. That's 30 degrees. We got tan 30 equals opposite over 0.5. That means this center of mass needs to travel 0.29 units for the object to tip. Here's another interesting point if you're a math nerd. If you have a four-legged stool here and you want to, or say a four-legged seat right here and you're sitting on this, you can cut this in half and represent this on a two-dimensional page and watch it tip over. You can't do that with a triangle though, because no matter how you cut this, you're going to have part of your triangle going into the page. So you're not able to accurately represent this on a two-dimensional page. So it took me a few minutes to figure this one out, and then I realized I could just turn my four-legged stool and three-legged stool into cylinders. And that's what I did right here. Take this, there's a leg on each corner, leg, 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 leg. There's a three-legged stool or three-wheeled vehicle here, leg, leg, leg. I just make a circle around the center of mass. Radius will be 0.5. Radius here will be 0.29. Or you can take the diameter. The diameter will be 1. The diameter here will be 0.58. And that means it'll tip with 58% of the force. I think it's kind of interesting to show how you can draw accurate scale representations here. So I just did, for a 2-to-1 ratio, I did 8 by 4 centimeters. This is for the four-legged stool, but for the three-legged stool, I have to keep the height 2, so we're still comparing apples to apples, same height. But the width here will be 4 centimeters right here, but it'll be 4 centimeters times 0.58. That gives me 2.32 centimeters across. So here it's 2-to-1 ratio, here it's a 2 to 0.58 ratio, and in actual centimeters, this is 8 centimeters by 2.32 centimeters. Another way to look at this is, if you're standing on a four-legged stool and hoping it won't tip, it's pretty stable. You got 2-to-1 ratio, that equals 2. If you have a three-legged stool of the same height and the legs are equally distributed, you'll have 2 divided by 0.58. So then that stool that's 2 feet high becomes, it will tip as if it is 3.4 feet high. So it's like it'll be taller with the same base, or you could just say it has the same height, but it has a narrower base, whatever. Next up, I want to see if this is a vehicle. How does this translate to if you're on the road and you want to take a curve? So I'll just do a formula, mv squared over r equals the force. This is for centrifugal force or centrifugal force. Let's just make mass and radius both equal 1. Now we just got v squared equals force. That means velocity equals the square root of your force. Arbitrarily make a force of 100 for our four-wheeled vehicle. Take the square root of that and you'll get 10. So that means if you take that corner with a velocity of 10, it'll tip. We can do the same thing here with a three-wheeler. Take the force needed to tip a four-wheeler, which is 100, but we only need 58% of that. 100 times 0.58 is 58. Take the square root of 58, gives you a velocity of 7.6, or 76% of the velocity around that same corner or that same curve, and you'll tip. A velocity of 10 versus 7.6 isn't really relatable. If you wanted to, you could multiply both of those by 10. So if you take a curve at 100 kilometers per hour in a quad bike, that means you could take it at 76 miles per hour on a trike before you tip. Or multiply them by 5. So 10 times 5 is 50. 7.6 times 5 is 38. So if you ride a quad bike around your house and there's a country road somewhere with a curve, and you always take it at about 45 miles per hour because you're an adrenaline junkie and like to get right up to the edge, you'll be fine. But if one day you get a three-wheeler and you do the same curve, you'll tip at 38 miles per hour or kilometers per hour or whatever.